married to a beautiful and fantastic woman who also happens to be a professor here. Since this is recorded, I have to be saying this. She's beautiful and fantastic. She was unfortunately called to Redwood City, California to take care of a sick aunt. She actually left Sunday and she's getting back Friday, so she would very much like to be here. But that's the first thing you need to know. The second thing you need to know is I have a fantastic family. My mother is still alive. My father passed away. My mother currently has pancreatic cancer. She's had it for 3 years. She was on hospice, and they took her off hospice because she was doing so well. So I have 2 sisters, younger, 5 nephews, a mother-in-law that's fantastic, brother and sister-in-laws that are fantastic. So I have a great family that I'm very, very proud of. The third thing is I have fantastic friends. Some of them are here. I play poker with them regularly. I am in a stock club with them regularly, and they keep me sane. And I'm very proud of my friends. The fourth thing is I drink gin. Occasionally. Now you caught me. I drink it often. But I don't condone the use of alcohol, but you just need to know that. I haven't had any yet today. The fifth thing is that I collect mechanical puzzles. An entire room of my house is devoted to secret puzzle boxes and sequential discovery devices and machines. I've never grown up. I'm in that room every night playing with my toys. And it is one of the finest collections in the world. But I've been collecting for 30 years. It's a pretty cool room. And the last thing, I love mathematics and I love teaching. And so you're not going to get any deep wisdom tonight. What you are going to get is some mathematics. Some elementary mathematics that's understandable to all of you. It will be understandable to all of you, I promise. But it's simple rules that lead to interesting behaviors. And so I'd like to start us off with, the title of my talk is Symmetry, Pattern, and Beauty, and I'd like us to start off with an experiment in symmetry. First of all, you should know there's essentially 2 kinds of symmetry: reflectional and rotational. Here's an example of each. If you look at box name at the top, you'll notice that it is symmetric about that line. That line acts like a mirror. Does everybody see the reflectional symmetry? Mozart, at the bottom, has rotational symmetry. Still Mozart. 180-degree rotational symmetry. These were designed by a designer in California named Scott Kim. And you don't have to be a musician to have your name inverted. There's me. There's me again. 180-degree rotational symmetry. So Scott Kim is a master at doing these. They're called inversions, and he's got a website devoted to them. So, the first experiment, you will need a partner. Each of you has been given 8 half words. If you put 2 papers together in the correct manner, you can create 8 full words. So I'll shut up for maybe 2 minutes, and we'll see how many of these 8 that you can get. So again, this is the experiment in symmetry. You might need to hold them up to the light with the 2 papers together.
Well, this is definitely oh, but this doesn't come down. Oh,
Every time I got a nice spot. Yeah. That's fun.
I'm assuming that most people have number 1.
Yeah.
It is what? Icebox. Here are the 2 pieces. There is icebox. What kind of symmetry? Rotational or reflectional? Reflectional around the horizontal axis. Did anybody get number 2? Is mirror. What kind of symmetry? Reflectional around the vertical axis. Number 3. The other number 3. Is echo. And reflectional symmetry. I heard this one. Number 4 is symmetry. What kind of, yeah, that's kind of bad there. What kind of symmetry? It's rotational. If I rotate it 180 degrees, it will remain the same. This is the one that I find the hardest. Anyone get number 5? Dance. Can I guess? Again, I find the rotational symmetry words a little bit trickier. I heard this one. Number 6, suns. Again, rotational symmetry. Number 7. Myth. Reflectional symmetry around the vertical axis. Number 8. I thought I heard it. Fantasy. So that's the symmetry portion of the talk. What I've done is I've gone into my archives and pulled out interesting, relatively easy, but beautiful things that are kind of unexpected. And I don't think the mathematics involved tonight is going to be above anybody's head. But most of what I'm going to do depends on a process called iteration. I'm going to look at various iterative schemes. So here's our working definition. Iteration refers to the process of taking something, usually a number, but not always, applying fixed rules. Hopefully they'll be simple rules, because the whole point of tonight's talk is to show you that simple rules can generate some really neat behaviors, unexpected behaviors. Applying fixed rules to the object to obtain a new object, and then applying the same rules to that new object to get another object, and to continue until something interesting happens. Well, what in the hell does that mean? Well, I have lots of examples about what I mean by something interesting. You can use the back of your page to perform the first iterative system. This is due to Ecker. Select a number. I have an example at the bottom, so you might want to hold off. Select a number, write the number out in English, count the number of letters used in the English wording. This is the new number. And repeat step 2. So here's an example with the year I was born. 1957. I wrote it out. 1,957. If you count the number of letters in the English, 1,957, you get 32. That's the new number, which I wrote out in English. Count the number of letters in 32, there are 9. And you continue until something interesting happens. Go.
Another pencil? Yeah. I'm unprepared for class. Thank you.
Has anyone seen anything interesting happen? My prediction is that you hit 4. In fact, any starting number will hit 4. It is called an attracting fixed point. No matter what number you start with, you'll wind up at 4. Now this does depend on the language that you choose. In German, 4 is, again, the attractor. Because German 4 has 4 letters. In Spanish, 5 is a fixed point. Once you hit 5, since cinco has 5 letters, you're there. But notice what happens if you hit 4 or 6. Spanish 4 has 6 letters. Spanish 6 has 4 letters. So you bounce between 4 and 6 if you would happen to hit 4 or 6. In French, you have an attracting period 4 sequence. 4 has 6 letters. 6 has 3 letters. 3 has 5 letters. 5 has 4 letters. You're back to 4. So you have this periodic behavior. Questions on iterative system number 1. In our language, 4 is the attractor for any starting number. Another iterative system. This is a famous one due to Luther Collitz. Play along. Select a positive integer. I pick 12 at the bottom there. If the number is even, divide it by 2. If the number is odd, multiply the number by 3 and add 1. That's the new number. And do it over. So I started with 12. 12 is even. Agreed? So I divided by 2 to get 6. 6 is even. I divided by 2 to get 3. 3 is odd. So I multiply by 3 and add 1. Does everybody see the scheme? 10 is even. Divided by 2. 5 is odd. Multiply by 3 and add 1. What happens? I'll shut up for 30 seconds. Try it. You could just... No, you don't get 4. Actually, you do. Actually, from 16, you're going to get what next? 8. And then from 8, you get 4. But wait, from 4 you get 2. From 2 you get 1. From 1 you get 4. From 4 you get 2. So it appears as if what is happening is that everything is sucked into that 4-2-1 period. That is an open question. If you can prove that any starting number ends in the 4-2-1 period 3 sequence, please talk to me. We can be rich. That's an open question. And this is what I like about the problem. Completely useless. If you're looking for some kind of application to this, that's not what I do. The more devoid of application the mathematics is, the more I like it. I'm more of an artist than a scientist. But this has been outstanding since 1937. The conjecture, and mathematicians essentially believe that it's true, is that it will always eventually reach 1. Some numbers go for quite a while. If I could put this up here. If you start with, this is the starting number 54. This goes 112 times before it hits the 421 sequence. It hits a high of 9,232. So again, this is the starting number 54. It's particularly dynamic. There's a graph of the numbers it assumes, but it eventually, after 112 iterations, hits the 421 sequence. It's unknown whether there's some number out there that doesn't eventually hit this sequence. Outstanding question. Any questions on iterative system number 2? This is one of my favorites, just because I'm a number theorist. This is due to Conway and Guy. It's a little bit complicated, so I'll carefully explain it. Here are 14 fractions. Nothing complicated about that. I've labeled them A through N. So here's the scheme. You start with 2. Multiply 2 by each fraction in the list, in order, from A to N until a new integer is obtained. Now obviously if you multiply 2 by fraction A, you get 2 times 17 over 91, which is 34 over 91, and that's not an integer. Agreed? So you go to B. Can anybody see what's the first fraction in that list when multiplied by 2 will give you an integer? It's M. Because 2 times 15 over 2 is 15. All right, so good. Until a new integer is obtained. You keep doing that. Okay, so now we have 15. You multiply 15 by each number in the list until you hit an integer. And you keep on doing that. So, multiply the integer by each fraction in the list in order from A to N until a new one is obtained. So from 2 we get 15 via fraction M. And then from 15, I have it on the next page here. Here are the 14 fantastic fractions again. And we start with 2. 2 times M is 15. And you'll multiply 15 by N. That's the first fraction in the list that will give you an integer. It's 825. Now we multiply 825 by each fraction in the list. E is the first fraction that will give you an integer. And you continue. Back to the scheme. You're only going to record the numbers that are powers of 2. So, that look like 2 to a power. So back to this. We start with 2. We get 15. 15 is not 2 to a power. Nor is 825. Nor is 725. Nor is 1925. Nor is 2275. But 13 more steps, you'll get 4. That's a power of 2. It's 2 what? Squared. Now you get 4. You multiply 4 by all those. You keep on doing this until you hit the next power. You only record the powers of 2. This is just amazing. So here are the integers that you get. The first one is 4. We've seen that one. It takes about 18 steps to get there. The next one's 8. And I don't know how many steps there are until you hit 8, but you're only recording the powers of 2. Let me put each of these in 2 to the exponent form. Look at the exponents. They are the primes. In order. These 14 fantastic fractions have the infinitude of primes encoded within them. And there are infinitely many primes, but armed with those 14 fractions, if you only record the powers of 2, you'll generate them. And not only will you generate them, you'll generate them in order. That's simply amazing. The mathematics is deep. By the way, the mathematics behind a lot of these things, what I just showed you an open question, is pretty deep. But you can easily understand what's going on here. Questions? That's my favorite one. I'm a number theorist and I work with prime numbers. All right. Iterative system number 4 comes in several pieces. This is due to Robert Devaney. I'm going to pick 0. Multiply 0 by itself. That's the new number. I repeat step 2. Okay, so we start with 0. Multiply 0 by 0 and you get? 0. 0. Very good. And then continue? 0. Boring. I know. All right, let's kick it up a notch. Let's Start with 0. Multiply the integer by itself and subtract 1. Subtract 1. Multiply the 0 by itself, subtract 1. What do you get? Negative 1. That's the new number. Multiply negative 1 by itself and subtract 1. 0. Multiply 0 by itself and subtract 1.
Negative 1.
And so here we have a nice little period 2 sequence. By the way, these systems form a branch of mathematics called dynamical systems. I'm going to get into some fractal geometry in a moment, but this is heavily involved in systems that are changing. Algorithms like this. Okay. So, you need a calculator for this one, so I have the results. What did I do? I picked 0 and just multiplied it by itself. That was pretty boring. Yes? Zeros. I took 0, multiplied it by itself, and subtracted 1. I got that period 2. Now I'm going to subtract just a little bit less, or a little bit more, however you want to view it. Multiply the integer by itself and subtract 1.1. Just a little bit smaller than 1, or bigger than 1, but we're subtracting. That's the new number. So, start off with 0. What do you get when you multiply 0 by itself and subtract 1.1?
Negative 1.1.
Very good. What do you get when you square negative 1.1, multiply negative 1.1 by itself, and subtract 1.1? Well, who knows? That's what you're going to get, 0.11. Now you multiply that number by itself and subtract 1.1. You get that number. And you continue until something interesting happens. Has something interesting happened yet? I haven't seen anything interesting. In fact, some more steps. Oh, maybe 500. Something interesting will happen. You'll get that number. And then you'll get that number. And then you'll get that number. And then you'll get that number. Forever. Another period 2. Just the numbers aren't so nice. You can actually compute what those are, but I won't bore you with that. But those are approximate. But once you hit 0.091608, you'll hit that other number, and then you'll hit 0.091608. Okay, great. Let's subtract 1.3. We squared. We subtracted 1.1. We subtracted 1. Then we subtracted 1.1, and now we're going to subtract 1.3. All right, so here we go. 0. 0 squared minus 1.3.
Negative 1.1.
Very good. What's the next one? Who knows? More steps. 500 or so. You'll get that number. Then that number. Then, oh, you're expecting period 2. That number. And that number again. So it's now period 4. What the hell? I mean, all we did was we descended. These are all parabolas, if you know about such things. F of x equal x squared is a parabola. X squared minus 1, that parabola moves 1 unit down the y-axis. Then x squared minus 1.1, it shifted down. But the dynamic behavior of the starting value 0, how can it be so different with such small permutations in the constant? Okay. Guess what? Select the integer 0. Multiply it by itself and subtract 1.38. So the parabola has descended on the y-axis even a little more. That's the new number. Any guesses as to what happens? 0. There, negative 1.38. Some more steps. Ooh, the font size just got smaller. Okay? Approximately. 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 Oh! We're back to negative 0.158801. Period 8. Okay, so from 1 to 2 to 4 to 8. What did we subtract there? Who remembers? 1.38. Let's subtract 1.395. Start off at negative 1.395. Some more steps, 500 or so. You'll get that. 15 more distinct steps. You'll get that again. I haven't written them out. Period, 16. What do you guess is next? Oh, look. Iterative system, 4.7. We were at 1.395. Let's go down to 1.4. So the parabola is descended on the y-axis to 1.4, negative 1.4. Multiply, same deal. 0, negative 1.4. Some more steps, you'll hit that number. What's your guess as to how many numbers it will be before you hit that number again? 31 more steps, so 32 including that one, and you'll hit negative 1.0889. And this continues until you hit subtracting 2. So if you subtract 1.4, there's some interesting behaviors between 1.4 and 2, but at 2, all hell breaks loose. And this is called the period doubling route to chaos. What happens with x squared minus 2 is unpredictable. The whole purpose of dynamical systems is to predict the behavior of systems that are changing. But the fact that such small permutations in the vertex of the parabola from 0 to negative 1 to negative 1.1 to negative 1.3 has such profound effect on what the system does. This is actually a branch of mathematics called dynamical systems, and we are trying to make sense out of the chaos. There might be patterns there that we can't see, but they're very, very difficult to find. Questions? Okay. You'll like this one. Oh, look. A big die. Sharon? Pick any point inside a fixed equilateral triangle ABC. We're going to play this. Roll a single die. Sharon has the die. If a 1 or 2 is rolled, choose vertex A. If a 3 or 4 is rolled, choose vertex B. If a 5 or 6 is rolled, choose vertex C. Proceed from the point on a straight line toward the chosen vertex. This will all be clear on the next slide. Stop halfway and plot a point. This is the new point. All right, so let's do it. Remember, 1 or 2, vertex A. 3 or 4, vertex B. 5 or 6, vertex C. An equilateral triangle. We pick a point. I'll just pick that one right there. That's the starting point. Sharon, roll that die. It's a 4. Who remembers where we moved? To B, halfway. So here's the distance to B, that's about halfway. That's the new point. So let me call this P sub 0, and I'll call this one P sub 1 so we can keep track. Okay, so great. Now obviously, if this sucker comes up 4 every time, or 3, we're just going to march in toward vertex B. Agreed? But probability dictates that's not going to happen. Okay, so your name?
Check.
Check. Roll, Check. It's a damn 4. Okay. Fantastic. Autumn. Or 9103 either. It's a 1. It's a 1. So we get to move halfway toward which vertex? A. Now this is hard to do, so it's P2 as our last point. Halfway between, puts it right there. Does everybody understand what's going on here? The question is, after 1,000 times, what are you looking at? If you plot all those points, you keep rolling the die, you plot the points, what are you looking at? Any guesses?
Circle.
A circle. Any other guesses?
More triangles?
Well, here I did it. I'm going to put this on a white sheet so maybe it shows up a little better. Here I did it for 10 points. The equilateral triangle looks just like it did before. There I plotted 10 points. No apparent pattern there. So I kicked it up to 100. Some things are happening, but it's unclear what. Why stop there? 1,000. Now you notice that there are some points that don't fall into the picture. This was done with Mathematica. Here is what happens after 10,000 iterations. And not content with that, I kicked it up to 100,000. And there's a pretty cool picture of the Sierpinski triangle. This is an example of a fractal. It's a self-similar shape. Inside the big Sierpinski triangle, you can find 3 smaller Sierpinski triangles. And inside each of those, you can find 3 smaller. But you can prove, and I've actually done this proof in classes, it's not hard to prove that the Sierpinski triangle is the attractor for this system. And it is the attractor. You can see some points that don't fall in the Sierpinski triangle. And what you're doing is you're looking at an approximation of the Sierpinski triangle, which is really close after 100,000 iterations. So pretty cool. Questions? Okay. This is my favorite one. I need a definition. This is the, has anybody heard of The Game of Life by John Horton Conway? Not the Milton Bradley Game of Life. No. This is the cellular automaton Game of Life. Okay, so what is a cellular automaton? It's a system. This is my last one, by the way, but it's going to take a little while, and I have a great thing to end. A cellular automaton is a system of cells, each cell of which possesses a number of different states of existence. The states, governed by rules, are frequently dependent on the states of neighboring cells. Okay. That's a cellular automaton. Here's the Game of Life. This is by the same Conway that had the 14 fantastic fractals. It's played on a square grid, each component square being a cell. Each cell has 2 states. It's either alive or dead. Live cells will be denoted black. Dead cells will be denoted white. Each cell has 8 neighbors. So there you see a cell denoted C and its 8 neighboring cells. Agreed. Here are the rules. There are 2 rules governing the states of the cells. A cell that is alive in one generation remains alive in the next, if and only if it has exactly 2 or 3 neighbors that are alive. The birth rule: a dead cell becomes alive if it has exactly 3 neighbors that are alive. So let me just put that up there for just a while longer. So you survive if you have 2 or 3 live neighbors.